Okay, so we're looking at rates of reaction here. We actually started looking at reversible reactions, then we kind of like went back a level really to focus a bit more on rates of reaction in general. And we're just looking at what kinds of things affect the rate of reaction. So, first of all, higher temperatures, com- different, com- different to pressure and or concentration is often what's talked about here and surface area, um, uh, temperature affects it in two ways. One, the reactants, these let's say these things here are moving around really really quickly, and so when they react with say these blue squares, they're going to be colliding with them with more energy, and so when they do that, there's more likely to be a successful reaction. But also, whether they're not, even if you ignore the speed at which they're moving, the collisions are occurring more often. So you're going to have, on the one hand, the collisions occurring more often, and on the other hand, each collision happening with more energy. So you've got to make sure to mention both those points when talking about temperature. Whereas concentration and similarly with pressure, you're just increasing the rate of the reaction. Sorry, you increase the rate of reaction because the collisions are occurring more often. The particles are not moving any more quickly, so they're not colliding with any more energy. They're just reacting, they're just colliding more often than they would have if the concentration or the pressure wasn't as high. Surface area is a little bit different. So what I've done here is I've kind of um, I've got sort of imagine I don't know like a block. I said like a block of magnesium. Let's say we've got a block of magnesium on the right here, and these are particles of acid, and they're trying to collide with it. The stuff in the middle, the particles of magnesium in the middle, won't get reacted with until the ones on the outside have reacted. Okay, and then eventually, once that one's gone like that, now this one can get inside. Now, if we were to break it apart like this, now these acid molecules can access a lot more of it at the same time. So if you were to, so I think the example I gave was that if I had a strip of magnesium in a flame, it's going to react quite vigorously. But if you take the same amount of magnesium as a powder and you sprinkle it over a flame, you're going to get a much stronger reaction. It's going to react much, much, much more quickly. So increasing the surface area will also increase the rate of reaction. Now, what we're looking at before that, however, was a slightly more advanced topic than that bit there. So once you've understood that, then you would go on to looking at reversible reactions. So um, we've got these two graphs here, and we need to understand them both. The both got time along the x-axis, and the y-axis we've got rate on the top and then amount at the bottom. So what it's saying then at the top is how is the rate of the forward reaction? We'll talk about what that means in a moment. The rate of the forward reaction changing with time, and how is the rate of reverse reaction changing with time? What is the reverse reaction? Well, that would, let's take this top one here, nitrogen reacting with oxygen, producing nitrous oxide. That would be the forward reaction. But also, because this is a reversible reaction, nitrous oxide will also react, will basically decompose and form nitrogen and oxygen. So as this nitrogen and oxygen is reacting and producing nitrous oxide, at the same time, nitrous oxide is decaying back into nitrogen and oxygen. So the reaction never finishes. It's constantly it's going that way, but it's also going this way at the same time. And you've got the four at the beginning. There's only nitrogen and oxygen, so there's only reactants. So you're going to have a high rate of reaction, and you're going to have a high amount of reactants. So zero products because nothing's been produced yet. But as the reactants start to go down because they're reacting, then the amount of products increase because they've produced the nitrous oxide. Now, as the nitrous oxide starts to be produced, it will start to react because that's the reverse of reaction. Nitrous oxide will turn back into nitrogen and oxygen. But the more of something there is, the greater the rate of the reaction will be because there's more of it to react. So if there's a lot of nitrogen and oxygen, then the rate of reaction will be high because there's a lot of it there to do the reacting. As it drops, as we lose the amount of nitrogen and oxygen, we're going to lose the rate of reaction at the same time. And then eventually, at some point, the rate at which the nitrogen and oxygen is producing nitrous oxide is equal to the rate at which the nitrous oxide is producing the nitrogen and oxygen. It's kind of a confusing sentence. I've highlighted it here to see where the nouns are, where the objects of the subjects of the sentences is. So the number of reactants decrease, the rate at which they continue to decrease also decreases. Now this is why. So hang on, I've skipped a bit here. So eventually, the rate of the forward reaction is equal to the rate of the reversible reaction. This is what equilibrium is known as. This is known as equilibrium, and that's why this top one, they must meet, because that's when they flatten out at which the rate is equal, and so if they're equal, then they're going to be equal on the same lines, whatever that is. Now, on the other hand, this bit won't necessarily meet. In fact, they would hardly ever meet. They'll meet for a moment and then cross over. And that's because the point at which equilibrium is reached is not necessarily going to be 50-50. It hardly ever is 50-50. In this case, it's mostly the products that get produced. Now, what we're going to learn about in a moment is how to change this point of equilibrium. And I've said so far that it can be changed by affecting the pressure, by changing the pressure and changing the temperature. But we're going to look at why would that happen and how will it happen. So I'll stop the video there as a brief intro, then we'll look at that final little bit.